Yeah. Good evening to all. Now, in the previous class, we have gone through the PMMC instrument. So, whatever the various parts in the PMMC instrument that we have seen. So, PMMC stands for Permanent Magnet Moving Coil Instrument. And here we are having the scale. Okay, the pointer scale starts from 0 to 10. So, this scale is there. And apart from that, we are having the spring will be there. North and south poles will be there. Okay, so these poles, nothing but these magnetic poles will provide the or produce the magnetic flux. And here we are using a current coil conductor. You can see in this diagram. So in this diagram, we can see the current carrying conductor. That current carrying conductor can be uh, carrying with the current. That current produces certain amount of flux. Okay, anyhow, the magnetic flux is going to cut by the current carrying conductor so that it experiences a force, so that it is going to make certain amount of rotation. So not in the case of rotation, we can say in form of deflection. So that deflection will take place as like that, so that we are going to have a deflection on the screen. Now we'll go through the various things. So it's a U-shaped permanent magnet we are going to use, and a light rectangular coil. So the coil is going to be as a rectangular form. Okay, and then which is molded or which is wounded on the aluminum former. So on the aluminum former, the coil is going to be wounded. So it will be used as a iron core. So iron core makes the field uniform as well as decreases the reluctance of the air path between the two poles. So that is the main why we are going for iron poles, right? And then the rectangular coil is supported by the jewel bearings. So jewel bearings are nothing but, so at the top and the bottom, we are going to make use of, so let us say, so this is the spindle, what we can see, a sharp edged. Okay, so these two are going to called as a jewel bearings. Okay, so the jewel bearings are going to be supported. So a pointer and control springs are attached to the spindle, so that in order to move the pointer on the scale or having the deflection on the scale, right? So aluminum former provide the support for the coil and provide the eddy current damping. So here we are using the aluminum former, so which is going to provide the damping for PMMC instrument. So because damping is required for in order to reduce the oscillations. So in order to reduce the oscillations, we are going to make use of damping. So these dampings are going to be nullified or reduced by the eddy current damping. So always the eddy current damping will provide the good or the best performance, right? A permanent magnet, it is made up of metal or alkino, so alnico, this kind of material what we can use, and we can have the low hysteresis losses for the material what we are using for the permanent magnets. And it is bent like a horseshoe, so it's just like a U-shaped magnet. It is a U-shaped magnet. So this kind of magnet we are going to use. Okay, and the deflecting coil is wound on the aluminum former, and control springs are made up of the phosphor bronze material. We have gone through, we have already discussed why you are preferred phosphor bronze material. Okay, so because of the various features of the phosphor bronze, we are preferring to manufacture the control springs with the help of or by using the material phosphor bronze. And they are arranged in arranged the spindle in opposite direction. So one spring will be in this direction and another spring will be in the opposite direction. Okay, so because of that, we are going to get the control on the controlling torque will be much more better instead of using single spring. So I already informed that the controlling torque is always present in the system. So that's why the point is always showing 0. Okay, so whenever the deflection torque applied, nothing but whenever the input has been applied, then it is going to overcome the controlling torque and it is going to settle at the final value. Okay, once the input has removed, then the control spring will act according as usual, because already it is in the operation. That's why the controlling spring will works, and then the pointer will comes to the rest position, nothing but 0 deflection position. So aluminum pointer is going to be used because aluminum is not going to disturb with any kind of other magnetic fields, and the scale is graduated and painted sheet on of aluminum sheet. See, on the aluminum sheet we are going to place the, so we are going to prefer non-magnetic materials, right? And dust proof case. So in order to protect from the environmental errors, we are going to make use of the dust proof case, as well as ebonite front panel can be used, and glass over the on the scale. Okay, and the principle, so as we have already gone through, the when the instrument is connected in the circuit, the operating current flows through the coil. So that current coil conductor is placed in the magnetic field, then it experiences a force. It experiences a force. So still many students are joining. Okay, let it be. Then, so as the current carrying conductor or coil is placed in the magnetic field, then the coil is going to be experience certain amount of force. So because of that force, the deflection torque will be produced. As the coil attached to the spindle also rotates, and hence the pointer moves the graduated scale. So keep in that mind, it's a graduated scale. Nothing but the scale is uniformly distributed. The scale is uniformly distributed. So that's what we have seen in the previous diagram. And now coming to the PMMC meter, nothing but permanent magnet moving coil meter. Why it is works only on DC? Why can't we use on AC supply? Okay, so as we know, we are using the meters, either DC, I mean, in the laboratory, MI meters or MC meters. So specifically, we are saying the DC meter, nothing but PMMC meters are working only on DC supply only. So why that we'll see. Now, if the current through the coil is reversed, what will happen? If the current flowing through the coil is reversed, then automatically the flux linkage, nothing but the right hand rule, will be changed. Accordingly, the torque is also is going to be gets reversed. So in order to reverse the torque, we can reverse the current direction. So current direction means instead of giving plus and minus, if you provide minus and plus, okay, then the torque is going to be gets reversed. So because of that reverse torque, the pointer will move in the opposite direction. So as this is the scale, the pointer will start from this direction. Okay, so the pointer has to move in this direction. Okay, if the current is gets reversed, then what will happen? The pointer will move in this direction. Nothing but the pointer will cross. Let us say this is the 0 position, this is the 10 position. So it will come from 0 to negative while negative sides. Okay, so the DC meters, whenever we are using in the measurements, then we need to prefer what kind of direction we are using. That is very, very important. Now, hence the pointer moves in the opposite direction, that is below 0. The pointer will go below 0. So, hence they work only with the current through the coil pass in a definite direction. Nothing but particular direction. Here we are preferring the DC direction only. That DC direction coil only or DC currents only will provide positive torque. Okay, if the current flowing through the coil is reversed, then normally DC will be represented as, okay, positive. Okay, negative DC means from 0, the DC value will be minus. So minus negative current will produce negative torque. So negative torque will produce negative deflection. So negative deflection means less than 0 value. So at the less than 0 value, we cannot read the final reading. Right. Now you can see the same, whatever the parts we have discussed. Okay, the scale, right? Full scale deflection. FSD stands for full scale deflection. Light aluminum pointer. Light aluminum pointer means that pointer should not having much more weight. It is lightweight pointer. It is a lightweight pointer because, as we said, it should not be burden on the what you can say, the meter should not be a burden on the measurements or measuring circuits, right? So if the pointer becomes more weight, means it will take more torque to move from 0 to the final position, right? So keep in that mind. Next, and there is a permanent magnet, north pole and south pole permanent magnets will be there. Okay, the springs, observe the springs, that here the end one E, it seems to be as E, it is a fixed path, it is a fixed one. So from this side, okay, one is of like this end is fixed, and another is of like this. and here this end is fixed. So like that. Okay, so how they are placed, right? And jewel bearings will be there. See, observe the jewel bearings, axle, nothing but spindle. So this is the aluminum former coil. Okay, and how the spindle. I mean, you just observe this diagram. Okay, so here you can find how the jewel bearing has been placed, right? See the same diagram in a three-dimensional manner, how it will be. So here, this is aluminum former. On the aluminum former, this copper wire has been wounded. So the copper wire will be there as a rectangular coil, as a rectangular coil. So normally, will in machines, DC machines, whenever you are discussing DC generator principle, you have discussed about the single loop coil. Single loop coil. So instead of using single loop, so single loop coil will produce single cycle, right? So like that we can have nothing but we can make use of more number of winding. So that winding we are going to be represented with the help of this thing, and permanent magnet will be there. You just observe the spring directions here. So the spring directions and how much amount of control deflection torque will be provided, that will be there. We can see from this diagram, right? The same we can represent in a pictorial manner. So force 1 and force 2, here you can observe F1 and F2 are there. Okay, F1 and F2 are nothing but the two forces acting on the coil. The two forces acting on the coil. So this orange color is a metallic former. Okay, on this the metallic on the metallic former the winding has been wounded. Then the north pole and south pole, between the north pole and south pole, the flux lines will pass from north to south, right? These flux lines are going to cut by the current carrying conductor. Here the current carrying conductor is nothing but the coil. So this coil is going to cut this current field, so that at one side, in the previous class I have shown one diagram. At one side we can have more amount of field, at another side we can have less amount of field. So there is a field variation or field density variation will be occurred. So because of this field density variation, at one side of the coil we will have more amount of field, at another side of the coil we will have less amount of field. Anyhow, the two fields are going to be provided with to make the spindle to rotate, right? And so here you can observe. So we can have, we need to derive how much amount of deflection torque are going to okay, view all, admit all, right? Yeah, సింగిల్ ఉంటే అడ్మిట్, మల్టిపుల్స్ వచ్చాయి ఎక్కువ వచ్చాయి అనుకో అడ్మిట్ ఆల్, వ్యూ ఆల్, నెక్స్ట్ అడ్మిట్ ఆల్. సో మై సన్ ఈజ్ taking your attendance, right? Nothing but admit is accepting your joining into the class, right? Okay, n is the number of turns in the coil, and L is the vertical length of the coil in terms of meters, and D is the horizontal length. So length and width we can have in terms of meters, and I amount of current is flowing in the meter. Nothing but this current will pass through the coil. That current we are going to measure. With that current we are going to produce the deflection torque, and beta is the flux density between the poles. So nothing but this beta is provide nothing but the flux density which has been produced by the magnetic poles. So north pole and south poles will be there, the permanent magnet poles will be there. These poles are going to produce the magnetic flux. So that flux value beta or B we can have, and alpha will be there, how much amount of angle made by the conductor with the magnetic field. So nothing but angle of deflection we can, like that we can say. And we can have galvanometer principle. So whenever the galvanometer field present in the radial direction, nothing but we can have alpha equal to 90. Okay, from the Lorentz force equation we can have the force equal to n, nothing but the number of turns in the coil, b the flux density, I nothing but the amount of current flowing through the conductor, and L is the length of the conductor. So product of these four along with the angle, sine of the angle. So this amount of force is going to be produced. Now at alpha equal to 90 degrees, nothing but at exactly perpendicular direction between the field. Now let us say these are the field lines. Now the coil is like this. Now the coil is like this. So we can observe the field lines and the coil are perpendicular each other. So nothing but angle between the field line and the coil is 90 degrees. Nothing but alpha equal to 90 degrees. So these 90 degrees we are going to substitute in this place. So that what is sine 90? Sine 0 is 0. Sine 90 is 100. Sorry, sine 90 is 1. So we can have the force equal to NBIL. Nothing but the maximum force we can observe at the angle made by the conductor is 90 degrees. Okay, that is nothing but F equal to NBIL. Now, torque. Torque is nothing but force into distance. Now we have calculated the force and we need to observe how much amount of distance is going to be taken place. Nothing but TD, nothing but deflection torque. TD stands for deflection torque. So this deflection torque is nothing but how much amount of force we have applied. Okay, that we have calculated NBIL and how much amount of distance made by the conductor. Nothing but D. So F into D that we are going to get. So we are going to substitute this value in the first equation, nothing but NBIL. So that we are going to get TD equal to NBIL into D. Okay, but the area of the coil is given by A equal to L into D. So here in this formula, NBIL. Okay, L into D. So L into D is nothing but area, nothing but length into distance. Sorry, length into, okay, what distance or what we can say width. So we'll have area, capital A. Okay, or small a here represented with small a. So TD equal to NBIA. NBIA. So N is the number of turns, B is the flux density, I is the current flowing through the coil, and A is the area of the coil. Area of the coil. So where here we can have a galvanometer constant, that is TD equal to G into I. Nothing but where G can be represented NBA, because number of turns is fixed. Number of turns in the meter is fixed. Nothing but in the coil is fixed. The flux density produced by the conductors are fixed. Sorry, by the magnet is fixed. Okay, and area is nothing but L into D. It is also fixed dimension. So NBA. Okay, NBA are the values or fixed values for a given meter, and only the variable is I. So TD is proportional to I. We can have the conclusion as like that. TD is proportional to I, where TD equal to G into I, where G is nothing but galvanometer constant, nothing but the meter constant, that is nothing but NBA. N is the number of turns, B is the flux density produced by the magnet, and A is the area of the coil. Okay, so for a fixed meter, for a meter or for a given meter, these three values are constant. So NBA are constant. Only the variable term is I. So the controlling torque. Now, how much amount of deflection torque we have produced? TD equal to G into I. Now we'll see how much amount of deflection torque is going to be produced. So TC equal to K into theta, where K is the spring constant. Where K is the spring constant. And theta is the angle of deflection. How much amount of angle made by the spring, that can be calculated. So at the steady state condition means the controlling torque as well as the deflection torque, both values are going to be gets equal. That condition is called a steady state condition. At this steady state condition, the controlling torque produced by the meter as well as the deflection are produced in the meter should be equal. So TC equal to TD. Now just equate. K theta equal to G into I. K theta is nothing but TC. K is the meter constant, sorry, spring constant. Theta is the deflection angle. And G is the, what you can say, galvanometer constant, and I is the current flowing through the coil. So K theta equal to G into I. Nothing but how much amount of angle we are going to get as a deflection. Nothing but at the pointer from this position, let us say this is the pointer. So on the scale, now this is the initial position. Now it has made certain deflection. Now that angle is theta. So how much amount of theta is nothing but Gi divided by K. So where G is NBA into I divided by K, meter constant, sorry, spring constant. So these are the terms. Okay, so theta is equal to, now we can observe for a particular meter G is constant. For a particular meter G is constant. For a particular meter spring constant K is also constant. So theta is directly proportional to I. Nothing but how much amount of current is flowing through the coil is directly proportional to the angle of deflection made by the pointer. Okay, so that's why the scale what we are using in the PMMC meter is uniform scale. So theta is directly proportional to I, or I is directly proportional to theta. So I already informed that any meter, that may be a voltmeter, it may be a ammeter, it may be a watt meter, power factor meter, any meter. Okay, whenever you are connecting that into a circuit, that meter consisting of certain amount of certain coil, that coil is, in that coil the current is passing. Because of that current, torque can be produced. The torque produces the angle of deflection, so that any meter will produce the uh, any meter will measure in terms of current. Okay, and it is going to be displayed or represented in terms of whatever the meter it may be. So how much amount of angle it has been made, how much amount of angle it has been made, that angle is proportional to the amount of current flowing through the coil. Okay, and on the scale, on the scale, that value has been calibrated. If theta is, let us say, 30 degrees, if 30 degrees angle is made by the meter, then according to 30 degrees in that meter, the scale has been divided accordingly. Now coming to see how voltmeter and ammeter. So voltmeter is connected across the supply. Voltmeter connected across the supply, nothing but how much amount of voltage is going to be measured between the two terminals. Voltmeter is nothing but the potential difference meter. So how much amount of potential difference can be applied between the two terminals. So always we should connect the voltmeter across the supply. So this is the supply, let us say plus and minus. Let us say certain amount of voltage we are going to produce, or we are going to give certain amount of what you can say, certain amount of voltage we are going to apply. That voltage we are going to measure with the help of voltmeter. So the voltmeter internal resistance, the voltmeter internal resistance Ri is high. Ri is nothing but internal resistance of voltmeter is always high. Nothing but it is going to obstruct, okay, the entire current, so that it is going to measure the amount of voltage which has been applied across the supply terminals. Okay, so it means that no current should pass through voltmeter. As we said, it is the load. Load is nothing but our application. So current should not bypass, as we already informed. So whatever the supply, that amount of current I is flowing, the same current I is flowing through the load, and the same current should be get back to supply again. Okay, now here what should happen? The voltmeter should not consume the current, so that it means that the same current, nothing but high resistance will be there, as it is having high internal resistance. So less, very less amount of current will pass through the voltmeter. With that current, we are going to get how much amount of voltage has been applied. So always the voltmeter is going to connect it across the supply, across the supply. Plus is at one potential and minus is at another potential. So between plus and minus, we are going to connect the voltmeter. Let us say in the circuit, if you connect the voltmeter as like this, plus minus. Okay, in this circuit, if I connect the voltmeter as like this, then what value it is going to represent? So the voltmeter represent which value? Okay, tell me in chat box. This voltmeter is going to represent the circuit diagram what I have written and what I have drawn. I have connected a voltmeter as like this. Then this voltmeter is going to represent which value? Tell me in chat box. V equal to question mark. Let us say I am going to apply 100 volts. The input voltage what I have applied is 100 volts. Now how much amount of voltage I am going to obtain at V? Yes, give the answer in chat box. Yeah, few students are responding. Zero. Can you say why? Less than 100. One someone is showing uh, one student is representing that is less than 100. Wait. I will just go through the uh, Vamsi. Can you unmute your mic? Can you say why it is less than 100? But everyone is saying zero. Someone is saying less than 100. Chaitanya is also saying less than 100. So someone has raised your hand. Okay, I will. Uh, how to unmute? Wait. Uh, mm, can anyone raise the hand once again? All muted. So less than 100 volts. Someone is showing. Fatherwale is also saying 100 volts. No, it's wrong. It always represents. One is showing Dhanush because voltage is not counted in series. Something he has written, so it shows 0 volts. So voltmeter will represent the potential difference. Voltmeter will represent the potential difference. So at this point we are connecting the voltmeter. Let us say at this point is connected to plus 100 volts. Okay, and this point is also at the same place, nothing but between here. If you connect any voltmeter, these two are in the same what you can say potential. So plus and minus, you will get difference in the voltage. Between plus and plus, you don't have any, because if you connect at the load another terminal, you will get plus and minus. So nothing but like this for circuit. Okay, so voltmeter, one terminal is connected to positive and another terminal is connected to negative. Then it will show 100 volts plus and minus. If you connect between plus and plus, what it will show? 100 minus 100, potential difference. Voltmeter is nothing but voltage is nothing but potential difference. What it will show? Potential difference. 100 minus 100 becomes 0 volts. So that's why voltmeter should never connect in series. Keep in that mind. Voltmeter should never connect in series. Okay, right. And here we are having one more diagram. I will just remove this, what you can say. Yeah. Now we can have fresh page. Now we can see. So here volt multiplier is there. So do you know what is the purpose of multiplier here? It is, uh, if the voltmeter is unable to measure the specified range, let us say this voltmeter, now I am applying plus and minus, it is able to, I am applying 100 volts, so that I am taking a 150 volts range voltmeter, nothing but this voltmeter will measures up to 150 volts. Okay, so here all the same 150 volts voltmeter I have used, but instead of giving 100 volts, I am going to give 250 volts. So 250 volts I am applying. In the earlier circuit, I have applied only 100 volts. I am using 150 volts, so that 100 volts can be read by the 150 volts voltmeter. But now how much voltage I am applying here? 250 volts. Now what is the range of my meter? 150 volts only. So it can measure only up to 150 volts. But what about the excess 100 volts? So I need to measure 250 volts. So 100 volts is going to get dropped at the resistor what I have connected. Nothing but this resistor is connected with in series with the voltmeter. So nothing but certain amount of 100 volts voltage is going to be dropped across this resistor. Nothing but so here, so 250 volts plus minus. Here 100 volts should be dropped and the remaining 150 should pass through this voltmeter. Okay, so these 100 volts voltage voltmeter, okay, nothing but across this, let us say if I connect any voltmeter across here, I will get 100 volts. So 100 volts plus 150 volts. These two are in series now. In the series, we can add the voltages. So this voltmeter will show 100 volts and this voltmeter will show 150 volts. So 100 plus 150, total 250. So the 250, that's what we have applied as an input. So by connecting an voltage multiplier, we can reduce or we can increase the range of the voltmeter. Okay, so keep in that mind. So anyhow, about this concept, we will discuss in detail at the last. So then, okay, so far what I have explained has been represented in the these slides. Okay, now coming to the ammeter. Now we are going to connect the ammeter in series. Nothing but ammeter is going to measure the current. Ammeter is going to measure the current. Let us say here also plus minus. I am going to connect 100 volts. So here it is at an amount of load. So as we have applied certain 100 volts of voltage, as the load has been connected in the circuit, certain amount of current I is going to pass through the ammeter. Is going to pass through the ammeter. Nothing but the total current should pass through the ammeter, so that the ammeter internal resistance Ri is always low. So as we know that in the low resistance path, the current will pass. In the low resistance path, the current will pass. Nothing but resistance can be defined as it is the opposing resistance is nothing but it is the opposing to the flow of current. Resistor opposes the flow of current. If resistance value is less, what will happen? More amount of current will flow through the resistance. So it is nothing but that how much amount of current is going to send to the load should be measured by this ammeter. Nothing but the total current should be recorded in the ammeter, so that we can get the entire current flowing through or sending to the load. So that's why always this ammeter is connected in series. Keep in that mind. We are connecting in series. Okay, let us say now if I connect this meter instead of here, now I am just making the continuation here. Just I will connect the ammeter here. Nothing but the ammeter has been connected in parallel with the load, as similar to the voltmeter how I have connected in the earlier diagram. Now let us say what amount of voltage, what amount of current is going to observed in the ammeter. Tell me in the chat box. So I will open the chart box. So now screen infinity amps. Hussein has said infinity amps. Screen wait. Infinity amps. Dhanush also said infinity. Keshav Reddy is saying infinity. So I'm having second screen. That's why I can see in my system also. Any other answers? The ammeter will represent how much value. The ammeter will represent how much value. So instead of connecting the ammeter in series with the circuit. If I connect the ammeter in the parallel to the load, how much amount of value it is going to show. Infinity amps means, what is meant by infinity amps? So the ammeter may have certain range. Let us say 0 to some 20 amps. Just I am saying 20 amps range. Okay. So is 20 amps becomes infinity amps? Any answer? Tell me in the chat box. So infinity amps current is flowing through the meter. What will happen to the meter? Respond in the chat box. If infinity amps of current is flowing in the meter, as you said, is infinity amps. If infinity amps of current is flowing through the meter, what will happen? The coil may burn. Yes, absolutely correct. Yes, the meter will burn out. Nothing but the coil will burn because the ammeter internal resistance is low. A low internal resistance is connected across the load. What will happen? The current is always preferring in a low resistance path. As the ammeter is having low resistance path, what will happen? The current will pass through the ammeter. So as you said, infinity amps of current is correct. You cannot say infinite, it's maximum current. The total entire current will flow through the meter. Theoretically, we can say infinity amps. So that what will happen? If that much amount of current is flowing through the meter, the coil in the meter will burn. So we should never connect the ammeter in parallel to the load. So always this diagram is nothing but we should connect. Always we should connect in series. So ammeter should be connected in series and voltmeter should be connected in parallel. So for this circuit, I can add voltmeter. For this circuit, I can add voltmeter. Right. So voltmeter should connect in the parallel and ammeter should connect in the series. This kind of circuits only we need to use. Right. And if you want to measure more range of or higher ranges of voltage currents, then we can use a shunt resistance parallel with the ammeter. So that what will happen? Certain amount of low resistance can pass. So a shunt is having certain amount of low resistance as compared with the ammeter. Keep in that mind. As compared with the ammeter. So ammeter the compare చేసేదానికన్నా ammeter internal resistance కన్నా shunt resistance తక్కువ ఉండాలి. సో అప్పుడు కరెంట్ ఏమవుతుంది? The total current I is going to pass through, few of the current is passing through the shunt and the remaining current is passing through ammeter. If ammeter is having less resistance, so the entire current will pass through the ammeter. So shunt will be cannot be used. So always shunt or SH resistance should be less than or internal. So internal resistance of meter కన్నా shunt resistance తక్కువ ఉండాలి. అప్పుడు shunt లో ఫర్ ఎగ్జాంపుల్ సో టోటల్ సమ్ 20 amps అనుకుందాం. Meter can measure only let us say 15 amps or let us say 5 amps. I will have 5 amps meter. So 5 amps meter లో పాస్ అవ్వాలి, రిమైనింగ్ 15 amps షంట్ లో పాస్ అవ్వాలి. సో అప్పుడేమవుతుంది? 20 amps is splitting into 5 amps through the meter and 15 amps through the shunt. అప్పుడు షంట్ రెసిస్టెన్స్ తక్కువ ఉంటే ఎక్కువ కరెంట్ ఫ్లో అవుతుంది. సో 15 amps ఫ్లో అవ్వాలి కాబట్టి మీటర్ రెసిస్టెన్స్ కన్నా షంట్ రెసిస్టెన్స్ తక్కువ ఉంటుంది. సో 15 amps will flow through shunt, 5 amps flow through meter. So 5 plus 15 again. సో ఇక్కడ కరెంట్ ఇక్కడ డివైడ్ అయింది. ఈ పాయింట్ దగ్గర కరెంట్ డివైడ్ అయ్యింది. 5 15 మళ్ళీ ఈ పాయింట్ దగ్గర ఏమవుతుంది? జాయిన్ అవుతుంది. సో కిర్చాఫ్ లా. సో అట్ దిస్ పాయింట్ ద కరెంట్ విల్ జాయిన్ అగైన్. సో 5 అగైన్ ఇక్కడ నుంచి వచ్చి కరెంట్ 15. సో 5 plus 15 అగైన్ లోడ్కు పోవాల్సిన 20 amps కరెంట్ ఫ్లో అవుతుంది. సో 20 amps is equal to 20 amps. Okay, right. The same what I said has been mentioned in the these things, right? So low resistance shunt is put in parallel with the meter. That's what I said. Now coming to the applications of MC instruments, or in the laboratories control panel to measure the voltage and current, we can prefer the MC instruments. Nothing but control panel means in the meter or in the circuit panel itself, we can place certain amount of meters. So let us say, best example in the laboratory we can have what you can few of the meters will be there, which has been fixed in the panel. So there we can prefer MC instruments. So in the workshops to know the values of voltage, current, power, etc., we can make use of MC instruments. Substations and power stations for measuring purposes, we can use uh, MC instruments. In irrigation pumps, automobiles. So these are the places where we can have MC instruments. Now, examples of MC instruments. So it can be used as a voltmeter to measure the DC voltage. It can be used as a ammeter to measure the DC volt or DC current in conjunction with the rectifier as multimeter. So we can have we can make use of as well as so voltage or current like that we can make use of. So it is also used as a flux meter or also used as a galvanometer. So why you are saying is a galvanometer means galvanometer is a zero deflection galvanometer we can make use or we can use for some applications. So zero deflection means the scale will be zero, the pointer will be at zero. This is the scale what we can have, positive side and negative side. So the pointer will move either this direction or either this direction. Nothing but from negative, positive to negative, we can have zero deflection. So if the current flowing from one direction to another, from let us say this is A to B. So if this is the current direction, pointer will move in this direction. Let us say, for example, I am saying, if the current is moving from B to A, then the pointer will give deflection this side. Nothing but if the current direction reverses, as we already discussed, torque will produce in the opposite direction. If torque is in the opposite direction, then automatically the deflection will be in the opposite direction. So these MC instruments can be used as a galvanometer also. And the advantages, it consumes less power and the scale is uniform. It's very, very important. The scale is uniform so that we can easily mention or we can easily note down the radius because the amount of angle of deflection is directly proportional to the current flowing through the current in the coil. So high torque to weight ratio. So always it is going to produce high torque as compared with the weight. So weight of the meter. Okay, range can be extended by connecting voltage multipliers as well as the ammeter shunts, right? And there is no hysteresis losses, and effective and efficient damping can be provided because we are using the permanent magnets. In the damping torque, we are using permanent magnets. So the same permanent magnet what we are using for MC instruments, the same permanent magnet can be used to produce the eddy currents in the coil to produce the damping torque. So there is need not to require, I mean, there is no need of additional magnet for producing of what you can say damping torque, right? And does not affected by stray magnetic fields. So as we are having a single magnetic field, so no other magnetic fields are going to be disturb this magnetic fields. And there are few disadvantages also there, and it is very delicate instrument, delicate in view of construction and needs accurate design and assembly parts. So whatever the design, whenever you are assembling all these parts, we need to take much more care. And errors occurred due to the aging of springs. So as we are go on using the springs life may becomes reducing, so that their spring tension may gets lost. Okay, so because of that, the errors may gets increases, and magnets may gets weaken due to aging. So the magnets may lose its magnetic strength or magnetic property due to the aging. So this is about the moving coil instruments. Now moving iron instruments are there. Just I will give introduction, and the remaining concept will be discussed tomorrow evening again. So can anyone give the response in chat box? Do you have any queries in the moving coil instruments? You can ask the doubt. Just I will end this presentation. Uh, no doubts, Chaitanya. If you are having any doubts, you can text me in the chat box, or else you can send a or text message in the WhatsApp also. I can clear. As once again I am saying, don't absent for the online classes, because we can have a provision to record the entire class. Even afterwards also you can have a provision to visit or view whatever the class has been happened in the online class. You can, that recording version can be listened by you, so that we can have a provision, but it will take 1 day time. So whatever the online class what I have connected right now, it is in recording position. It will take 1 day to convert into the MP4 formats. So that file you can observe. So okay, from that you can note on the notes also. So in order to complete the syllabus, I need to go for the hybrid mode. Nothing but physical classes will be taken, as well as the online classes also will be taken. Okay, so to complete the syllabus, you have to bear with these things, right? And do you have okay, one question, sir? Moving coil instrument is used only for the DC measurement? Yes, as I said, in the DC coil, in the nothing but in the DC supply, if you reverse the current, so terminals plus minus, instead of that minus and plus, what will happen? Current will produce in the opposite direction, I proportional to theta. If current becomes negative current becomes negative, then automatically torque theta is also becomes negative. Are you getting my point, Danush? If current reverses in the DC, plus minus normally we are using positive terminal at one side and negative terminal at the other side. If you reverse the terminals, plus and minus and plus, then what will happen? Current will have negative direction. Current will have negative direction. Negative current will produce negative torque. As we have derived the expression, theta is proportional to I. If I is negative, then automatically theta also becomes negative. Then meter will give a negative deflection. So if a negative deflection is there, the pointer will move less than zero value. Then it is not possible to say how much value that you have, what you can say, it has been recorded. So negative, we don't have any scale. So that's why permanent magnet moving coil meters are used only for DC measurements. We cannot use for AC. So MC stands for DC. That's all. MC for DC. So blindly you can remember. MC meter, moving coil meter, DC supply, DC. MC, DC. It's a rhyming word. Okay, you keep in that mind blindly. Because current reverses means torque reverses. Torque reverses means deflection reverses. Right? Any other doubts? Sorry, explain the advantage of moving coil instrument over moving iron instrument. Okay, I will explain this after covering these moving iron instruments. Right? So there are few advantages of moving coil instruments are there, and there are few advantages of moving iron instruments are there. We cannot say which is superior. Okay, but moving iron instrument is having a provision where we can use both for AC as well as DC. So comparatively, moving coil instrument, moving iron instrument will have more advantages. But preferably for better or good results, AC moving iron we are preferring, for DC moving coil we are preferring. Anyhow, after covering moving iron instrument, we'll get a clear differentiation between these two. Is it okay, Mr. Hussain? So your chart is also recorded. I will post your chart in the WhatsApp. I will provide the attendance also, which student has attended for how much duration. It will be provided by the Google Meet itself, right? So Google Meet will record your attendance, how much time you have been in the class, including minutes. Okay, so keep in that mind. So don't switch on, just attend and leave. Don't do like that. You listen the class carefully. Still, if you are having any doubt, you can send the chat box, or else we will go for just introduction about moving iron instrument for 2 minutes, because we have started the class at 7:10, because few of the students are gone joining. So, do you have language program tomorrow also, or tomorrow is a holiday? Language, I mean, foreign language classes are happening now, or the foreign language classes are scheduled tomorrow or not? Yes, it is there. So you don't have any holiday for tomorrow as of language classes are concerned. Is it correct? So college is holiday, but your language classes will commence. Is it correct? Yes, right. Okay, so that again tomorrow evening we'll continue the moving iron instruments. Okay, so the same link you can make use of this, and you can have the, what you can say, next concept, right? Just I will go through. Just observe this animation. That's enough. What is moving iron? So in the first part of the diagram, opposite poles attract. Opposite pole attract. So north, south. So you just observe the diagram. North, south are changing. Observe clearly for 1 minute. Opposite poles means north, first magnet, second magnet south, or first magnet south, second magnet north. So north and south will attract. So plus stands for attract. Okay. So north south or south north. So in this first part of this animation, you can have north south, south north. Observe the diagram clearly. So attraction will takes place whenever the two magnets are in opposite poles, north south, south north. Observe the same poles. So north north. So first magnet north and second magnet north. First magnet south, second magnet south. So here I will represent minus. So this minus stands for repel. This plus stands for attract. So moving iron instruments are having two types: attraction type, repulsion type. So in the attraction type, north south, south north, like methods can be used. In the repulsion type, north north, south south can be used. So moving iron instruments are of two types. One is attraction type moving iron instruments, and second one is repulsion type moving iron instruments. So you know about magnet, how the two magnets are going to attract, and how the two magnets are going to get repelled. So with this, we can have the explanation of moving iron instrument in the next class. So tomorrow at 6:30 sharp. So better to join by 6:20, because so all the students are continuously joining. So up to today I have started 7 o'clock, but still you have joined at 7:10. Even at 7:40 also few of the students have joined. Okay, so maintain the timings. So with this, I am going to end this presentation. So still, if you are having any doubt, you can ask me. Now I am stopping the recording also.